everyone, I hope that you're all doing well. In this lecture, I want to discuss the theory of sampling with you. You'll notice that in this set of lecture slides, I go over some material that I'm not going to discuss right now. This material was recorded and posted at this playlist. I basically got a little bit behind pre-recording some of these lectures and opted to just use the live recordings from the version of this course recorded in spring 2023 at UW-Madison. So that's where that's basically the source of the lectures on two-way tables, and it also goes over some of the review. I'm recording these lectures in part for this particular class and in part as part of a portfolio of teaching I'm developing. So I don't want the lectures to be too specific to like a actual class format. But at any rate, I went ahead and recorded that review lecture. So I'm not going to go over the review material if you're in my class right now, or if you're watching this in the future and you just want to see that review material discussed, please go to the previous video. But I'm going to jump ahead into sampling, which I did cover at the the end of the last taped live lecture, but I want to start basically at the top here and then go through it. So I'm actually going to skip ahead here, realizing that I'm probably going to give some people vertigo. Let's dive into the sample theory here. So here's the key problem of statistics. We want information on the population, but we only have data in most cases on a sample, which is a subset of individuals in our population. So our goal is to do inference about the population using the sample. And that's really what the second part of this course is all about. So we've learned a lot of descriptive statistics, and we're actually more or less out of things to learn about descriptive statistics at this level. Regression is a little bit of a formidable technique, even though it's very interesting and fun. And it's not going to get more complicated than that. Now we're just going to learn, okay, how reliable is a regression slope, let's say, when we not only don't, have a perfect match between the y and the x variable, but we also don't have information on the population itself. We have information on a subset of it. So today we're not really going to focus too much on that problem of inference right away, although this lecture sets that up, but we're going to talk more about the methodology of sampling. So here's the concept. First, I want to discuss something a little bit tricky here. Remember that population doesn't always literally refer to a group of people. So a lot of times it refers to a property or tendency. For instance, if we want to do inference on the relationship between race and income in the US, and we're not concerned with, some exact second, maybe we have data that are gathered themselves over months, so a survey takes some time to unfold, the exact population of people changes. Some people die, some people are born, some people leave or enter due to immigration. Those are actually really the only sources of population change. That's a fundamental equation in demography, in fact, but still, that's four sources of change that could be operating with great rapidity at different times. So when we talk about the population, we're thinking more about some kind of stable, cohesive sociological unit. So even if the exact people living in the United States changes, second to second, probably between the time I started that sentence and the time I'm ending it, it's changed. But still, we can say, well, it's a fairly cohesive unit. I'm going to assume, or assert would be a better way to put it, that there is a kind of stable identity from, at least maybe a year, over the course of a year or something. So that's how I've defined the population parameter here. I wanted to note a little bit of jargon here. So do be aware of the fact that we need to be a little bit consistent in how we refer to things. So when we talk about population level constants that we hope to do inference on, those are called parameters. And you can remember that it goes with the population because it also starts with a P. And their realizations in any one sample are called statistics. So S statistics also goes with S sample. Generally speaking, we use Greek letters, such as those listed here, to refer to parameters. For example, mu means the mean because it makes the M sound. S means the standard deviation because it makes the S sound, and so on. Also, I haven't shown this yet in this class, but rho is the correlation coefficient, presumably for a relationship. I actually don't know the origin of that, but note that this is a Greek, even though it looks like a P, it's actually the Greek letter R, and it makes the R sound, hence rho. So they all kind of have some meaning if you do forget. You don't need to memorize this entire Greek alphabet. This is from a textbook on vector calculus where you really do need to know all of these things at certain points. And this is, as far as I know, the entire Greek alphabet. But you want to know for this course some of those key ones that I just mentioned. We'll get to know a couple more. We'll learn that pi sometimes has different meanings. We've seen beta and alpha. We'll probably discuss at some point delta and epsilon and theta. So we don't need to know all of them, but a fair number of them. Chi will also come up as well. Okay, so that's just a brief side note on those things. So let's talk about samples. So how do we produce samples well? Well, we should generally avoid certain bad sample designs, and that's actually kind of a nice way to think about what it means to sample well. So let's talk about two common problematic designs. These would be convenience samples, basically just asking whomever I can spot hanging around, and self-selected samples. And the book that we're using more at all calls these voluntary response samples, but most surveys are voluntary in the sense that the person chooses to participate or not. It's actually kind of a problem in general. Not that people shouldn't have the right to opt out, of course, but it's actually a really general problem that people who end up in samples at the end are people that want to be there in some sense. They're not people that actively don't want to be there. So that's actually a really deep problem. A more specific problem is cases where people also enter the sample by their own volition. So I'm actually just realizing this as I'm saying it out loud, but a nice way to summarize this would be there's a problem that no matter what method gets people into a sample, there's the problem that people tend to only stay in the sample if they want to. But there's this kind of extra problematic design where people also aren't even getting into the sample at random, they're self-selecting into it. So that's actually kind of a nice way to put it. And what happens in both of these cases is that we have bias. So we have a sample that's not actually representative in some sense of the underlying population. So why is it that good sampling design is what's known as a simple random sample? So why would randomness be desirable here? Well, the point is that when you have a simple random sample, the difference between your sample statistics and your population parameters is also random. So for instance, any given sample mean, let's say of the population education, so sample mean estimating that population mean is going to be wrong, of course. It'll always be a little bit wrong, but it's not going to be wrong in any particular direction. It's unbiased. So we don't know for any given sample whether it's going to be bigger or smaller. Whereas conversely, like if we think about the case of a self-selection into a, let's say a poll that's hosted on a news website that asks about who you're going to vote for, we know that this is going to, generally speaking, capture people who tend to be a little bit more politically informed, and that would be a good way of saying it, or also possibly politically a little bit more tending towards extreme or kind of hardline beliefs. And there's all kinds of other examples of that. So let me just pick one other example. If we think about, let's say, a Twitter poll that a fitness influencer puts out, and I'm not picking on fitness influencers. I'm on fitness Twitter, so I'm just thinking about some of the things I encounter that are clearly not scientific. And someone asks, how often do you work out? Obviously, if you're following someone who posts about working out often, unless you're just getting your feet wet, you probably work out more than the typical person. So we could actually say in the, from the outset that this is going to be probably an overestimate of the population propensity for working out. So that would make it a biased sample. So what's so cool about unbiased samples? Well, this is the key idea, and this is actually the key idea that we're going to keep coming back to throughout the entirety of the course. So don't worry if it doesn't quite make sense. I'll show it about 50 more times, but I just want you to get an intuition here. So the intuition is this. Imagine that we have a variable that has a skewed population distribution. So let's assume here that we have a, information on the population. And in this case, I use the CPS 2019. And let's say that I know this is the population. So let's say I have a small city, and it's a city of 4,200 people effectively. And even though it's a sample, it's the CPS, just presume that this is the population of a small city. I think Garnett, Kansas, where my grandparents used to live, has about that many people. So maybe we're city planners in the city of Garnett, Kansas, and we're trying to, maybe we have this kind of population level data. And we know that wages in our city are skewed, right? So what if we wanted to use a sample from the city? Let's say we now don't know the city population. What if we wanted to use a sample to estimate the mean wage. Now, the underlying variable is skewed, right? And so we might think, okay, well, what if I could somehow, by taking a sample mean, say something about how that mean would be distributed across many possible samples? And then maybe I could use some of my tools for describing probability density functions, because since the mean can take on any value, even if you only have, even if the underlying variable is discrete, a mean of it can take on, in theory, an infinite number of values. Then, you might think, okay, well, what if I could use that probability density function to say something about that distribution of the sample mean? So for instance, what if I could say, well, if the true mean is this, then the sample mean I have would be relatively probable or relatively improbable. Or this range of values would be relatively improbable or probable. And it turns out that because the sample mean differs from the true population mean only through random error, if we do have truly random sampling, that means that the sampling distribution, in other words, the distribution of samples or sample means across all possible samples, which is a theoretical concept, right? It doesn't actually exist. We only ever take one sample for the most part. I mean, people resample the same population all the time, but any actual research project is probably just going to use one sample, and sometimes you don't have this resampling. But the idea is that the sample mean that you have is drawn from a distribution, a theoretical distribution, that is basically all possible sample means. So what does that distribution look like? It turns out that that distribution looks normal. And the reason for that is that if you think about it, and it's first of all also centered at the true population mean. So this is what that sampling distribution looks like for this fictional city here. And we can actually simulate that in Stata. So I simulated taking, in this case, basically, I think how many? Yeah, 500 samples of 500 people. And so I basically told Stata pluck from this small city, quote unquote, a sample of 500 people, take the mean of the salaried workers there, and then basically repeat that 499 more times, and then plot a histogram of the means from all those samples. Notice that this is normal looking, unlike this, which is very skewed. And again, the reason is that it's actually pretty intuitive if you think about it. There's no reason for these sample means to differ systematically from the true sample mean, which would be somewhere over here, right? So that means that the farther they are from the true population mean, the less probable they are, right? So you're unlikely to get a freakishly high mean, 38, when the true one is 33, unless you just have a really atypical sample. Whereas we can see that the bulk of the data are really close to what we actually happen to know is the true population mean here, and that makes sense because if they're only differing through random error, it's more likely than not that the error is going to be like that the bulk of the data will be pretty close to each other because you're just as likely to have a small negative error as a small positive error. And basically the idea is that there's no preferred direction for the error, and the likelihood, or let me say that more exactly because likelihood means something specific, the probability of an error is inversely proportional to its size. So the probability of a large error is small, the probability of a small error is large. So that's what's known as the central limit theorem, and we'll come back to that many times in this course. But I just wanted to kind of give a intuition for that, since that idea is very heady and oftentimes takes a long time to set in. So I just wanted to mention it before we get too much further in the course. I also wanted to mention, and I'm going to fix the slides here while I do this, I wanted to mention some kind of common pitfalls here because there's a variety of reasons that you might think this still shouldn't work. Like there still should be a better way. Random samples are a little bit too, we're throwing caution to the wind. It's random after all. So why doesn't something like quota sampling work? And I mentioned this also in part because a version of quota sampling that we'll meet in a little bit is actually quite useful, but we have to be very careful about how we do it. So quota sampling means trying to get a proportionate number of people into the sample from each relevant group. And it seems like a good idea at first, but it fails because there's one, no clear point at which one should stop stratifying, and two, it doesn't offer an algorithm for picking within the selected strata. So in other words, if we think about like, well, okay, I want to get into my sample, let's say you're thinking about a case where you are again sampling on income and you're trying to do quotas. So you say, okay, well, there's white people and black people and Latino people and people of Asian descent and so on in the United States. And I'm listing all these ethnic groups. Okay, I should try to get a certain number of people from each group. And okay, well, there's men and women and there's people that identify as other genders. So I should try to get all of those people. And then there's people from the South, the North, and so on. And you can kind of see there's a potentially infinite list here, right? There's this really tricky problem that you would have to enumerate all possible relevant characteristics. So that's what I mean by saying there's no point at which we should stop stratifying according to this theory. And then two, how do you pick people from within that group? So one thing that pollsters used to do is, and pollsters, we shouldn't we shouldn't indulge in what the social historian E.P. Thompson called the enormous condescension of history. So I don't want to sound too smug. It's not like pollsters of the past didn't realize these things, and they were actually really, in some ways, adroit in their attempts to deal with these problems. But ultimately, at the end of the day, what you had were people saying like, well, okay, I'm a relatively wealthy white person employed by a newspaper. I should probably try to go talk to some black working class guys about who they're going to vote for. But the problem was within that general stratum, basically, they were just using social networks, right? Or they were just using people whom they knew or people whom they could contact easily. And that turns out to introduce a pretty specific kind of bias, right? So I wanted to give a particular example of this. This is, of course, Harry S. Truman. Maybe I actually shouldn't say, of course. The last time I showed this, hardly anyone knew who this was. I'm a little biased because he's also from very near my hometown of Kansas City. My mother and I and my stepdad actually went and spent a full day at the Truman Museum, or the Truman Library, I should say, over this winter holiday. So I saw this photo blown up to a size larger than my own person. But anyways, this is one of the most famous examples of pollsters getting it wrong. So you can see here Dewey, who is the Republican candidate in 1948, I think the year was, probably should know that, was predicted to beat Truman based on faulty polls. And they, back in the bad old days, had to print the newspapers before, the day prior. So they were so convinced, this is a Chicago Daily Tribune, big paper, were so convinced that Truman would lose that they printed it up. And of course, this is this famous photo with Truman having this S-eating grin, we would say, in Kansas City. So yeah, probably the most famous quota sampling fail, but there's many others. So here's a nice discussion of this from Dennis DeTurk, the mathematician. I would, take a look at this if you want. The idea is, basically just all the stuff we've said out loud, but I think this is a particularly interesting sort of study. And, I think Professor DeTurk's, discussion at the very end here is a nice way to break it down generally. So generally speaking, human intervention in choosing the sample is always going to be subject to bias. There's ways of trying to downweight certain kinds of bias, but you tend to then upweight other types of bias. So that's the basic point. So randomness guarantees some very cool results, but even well-designed studies can have significant problems, and I want to discuss a couple of the major ones: undercoverage and non-response. Undercoverage refers to a situation where we leave people out from the sample from the outset. So we typically fail to include them in the sampling frame, the total list of people we try to contact. For example, if someone is without stable housing, they're probably not in most lists of people whom surveyors would contact, and thus they are left out of the sample frame. We also have non-response, so people whom we do contact fail to reply at high rates or in systematic ways, or both. And this can be item specific, as you'll see in the homework if you're in the class. So I wanted to discuss two major causes of undercoverage and non-response that have to do with how we carry out surveys via the telephone. And these are respectively the lack of landline usage, which leads to undercoverage, since many sample frames are drawn from telephone books, even still, or lists of telephone numbers, and the ease of non-response with mobile phones, which leads to non-response, or just it is a form of it being convenient. There are other causes, as I mentioned before, this business about people without stable residence being rarely captured in a sampling frame. Non-response generally has a class bias, but why don't we investigate these two just to make this feel a little bit more concrete. So you can see here in the first case, response rates for several notable surveys, including the GSS and the CPS, both of which we examined in my class, have been declining, although it's not maybe as severe as some people might suggest. And one obvious source of that is the fact that you can see here spending on cell phone service has greatly outpaced. In fact, it's going in the opposite direction as residential or landline service, meaning that people use their landlines less and less. We've also got another source, though, that I did mention just a moment ago of non-response, which is really fascinating. So in this case, some researchers looked at non-response to an important source of income data, which is the CPS. And what they did was they used some restricted data to link the CPS to tax records. So you can see here that they have on the x-axis for various questions about income, earnings overall, earnings for full-time full-year workers, and average hourly earnings. The rate of non-response to this question on the CPS as a function of someone's administrative records income. And so you can see that in kind of a really fascinating way that seems to confirm a lot of sociological hypotheses, both the very poor and the very wealthy, generally speaking, or we should say very high income to be really exact, had high rates of non-response. So the people that were actually most likely to respond were your kind of proverbial middle class or stable working class individuals. So right here, this is, I think, the most striking graph. You can see both men and women who earned about median income had about the highest probability of responding. And then people in the, say, bottom decile here had somewhere, about double the probability of non-response, about, 17 to 34, or vice versa. And it also got pretty severe at the tail end of the distribution as well. So that's something to be mindful of. Now, in this case, these actually sort of balance each other out in a funny way. Although there's a lot more people down here, but the incomes are higher up here. It's actually kind of interesting to try and estimate that effect. But at a minimum, you should know that you're not getting the kind of actual data that you might believe yourself to be getting. So I wanted to mention a few other problems that can arise with surveys. One of them is social desirability response bias. This refers to the tendency of people to reply in a way that they believe a researcher wants to hear. And we actually just saw a case of people not responding for this reason, basically, but sometimes people also respond actively, but in ways where, and they may not even be aware of this, they are attempting to meet the researcher's expectations in some sense. And it's kind of interesting to think about this because many of us don't realize how much we're all people pleasers. We're social creatures, and we, generally speaking, shy away from too much overt social conflict when it can be avoided. And many times that results in people modulating their responses slightly. One way to think about this is just, you may not have filled out a survey anytime recently, but think about the last time you went to the doctor, right? Did you, describe some of your habits in a way that might be not even necessarily trying to make yourself look good as much as to avoid sanction, right? You don't want to look bad actively. Another possible problem here is wording effects, and this basically kind of is almost the opposite. A researcher indicates actively, or it's not the opposite, it's a compliment. The researcher indicates actively that they might want a particular response, or they at least say something in a way that would imply that, even if they don't want that. And we'll see in a moment that both of these are pretty serious problems. So here you can see this is a case of social desirability response bias, setting aside the fact that samples don't, as we've been discussing this entire lecture, always accurately represent the population. If we assume that sampling error is relatively small here, we would assume that the true voting behavior in the 2012 presidential election, as asked about on the 2018 GSS, would be north of 70%, maybe 72 or 3. But when you actually look at data, again, that comes from more of like an administrative source, notice that in 2012, the actual share of people voting in the presidential election dipped below 60% here. So pretty significant difference, maybe on the order of like 15% or percentage points, I should say, not percent. Now, again, some of this could just be sampling error. Some of it is also probably recall because this is a significant gap, more than 5 years. But at the same time, we also know that there's a strong kind of social inducement to vote. Even people that don't vote for principled reasons oftentimes are looked down upon. And especially if you voice the opinion that you simply don't know or would rather not know, this is obviously subject to great social sanction. So it makes sense that people probably would also tend to overestimate whether they voted or overreport this. Here's an example of some wording effects. There's a lot going on in this graph, but basically a researcher took a look at GSS responses to various social questions and asked respondents to say whether or not there was too little being spent on a particular issue. And you can see that these are split ballots. So basically, some respondents got a question about halting the rising crime rate, and other respondents got a question about law enforcement. And note that and the GSS does this on purpose, by the way, just to kind of do a little bit of a robustness check. Note that when you ask people whether or not they think there's too little being spent on halting the rising crime rate, many people would say, well, yes, of course, in part because this question implies that there is a rising crime rate, whether or not that is always true in the year that it's asked. In many years, it, of course, would kind of have to be false unless the crime rate is just simply going up over time. Definitely goes up in times, but it's not monotonically increasing. So sometimes this is actually providing respondents with false information. And of course, that induces them to be more supportive of more spending than just the generic phrase law enforcement. We'll see an example with assistance to the poor welfare in just a moment. So here you can see my calculation using the 2018 GSS. And again, you'll see an example like this in your homework. You can see that when people are asked whether or not we spend too little, too much, or the right amount on assistance to the poor, north of 90% of people are saying we spend about right or too little on assistance to the poor. But the share of people that say we spend too little or about right on welfare is, probably about maybe 60% or so. So there's a really striking difference there. And again, that's because there's certain connotations with welfare that don't exist with assistance to the poor. Now, some of these wording experiment questions are kind of cheap because they're not really asking about the same thing. But I would say, as someone that knows a lot about this issue, really, if you break it down, welfare and assistance to the poor hardly mean much different if you really ask people to think about it. You can say sometimes people use them in a technically different sense, but if you ask a regular person, what do you mean by one? What do you mean by the other? They're pretty similar. So a lot of this just has to do with these kind of gut inclinations that people have. So most studies are stratified random. Take it one more time. So let's wrap up with a discussion of the kind of complexity of sampling. So we've talked about, kind of what can go wrong even in the best designed samples, but I also want to introduce this fact that most studies are actually not simple random samples. They're stratified random samples, which have an element of quota sampling. So a stratified random sample first breaks the population into strata, then we sample randomly from within, taking different shares from each group to get desired n's. Little n here means sample size. Then we combine. The reason we would do this is we generally, want a certain subsample size from each group, but we may be unlikely to get a subsample size that's sufficiently large from groups that are small in the first place. So then at the very end, we weight people from those small groups to undo this overrepresentation. So what would that look like in practice? Let me give a discussion here from Matthew Salganik's book, which is a really good book called Bit by Bit. And here he uses this example of sampling for to determine the unemployment rate in different places. He uses kind of a silly example here, I think, because he's talking about Florida and California. A better example discussed elsewhere in the book would be if you had, say, Rhode Island or Wyoming, really small state, and you want to get a certain number of people from that state, and your sample, say, is only, let's say you're going to have a very small sample of, say, only 100 people. You may be very unlikely to get anyone from Wyoming just by randomly calling telephone numbers throughout the nation. But you may want to make sure to get a certain number of people from Wyoming in there. So what you would want to do in that case is strategically call more people from Wyoming, which gives people from Wyoming a higher probability of appearing at the sample. And then at the very end, you would want to undo that. So here's how you can undo that. Basically, you are going to write out this formula, which is a formula for the mean of the unemployment rate in the sample that adjusts for this over-inclusion. There's a way to do a bit of a sanity check here. So this pi I here is person I's probability of inclusion, and it's given by little n, or the sample size, over big N, which is the size of the population. So for example, let's just say you have a really big sample where you're taking 1% of the population. Little n over big N would be 0.01 or 1%. And setting aside the probability of sampling with and without replacement, which we don't need to get into here, you can say that every person had approximately a 1% chance of ending up in the sample. So then what you could do is multiply both top and bottom by little n over big N, which is what this pi I would be equal to in that case. And then what we have happen is those two things cancel here, and then we have in the denominator little n over big N, and the big N goes over here, and the little n stays in the bottom, and we just have the formula for the sample mean. So what would happen instead if someone had a higher probability of being included? So their personal probability is larger than that of the sample. Let's say they had a 10% chance of being included. So we weight them by a number here in the denominator that's larger than that of other respondents. So we are effectively getting rid of some of their influence. I wanted to show what that looks like in practice. So the GSS and CPS that we use in our class are in fact stratified random samples, for instance. So to the right is a bit of discussion about how weights work in the GSS from the codebook from 2019, the A appendix. You don't have to know this in too much detail for our class, and we actually aren't going to use sample weights, but I wanted to show you that even these samples that we've looked at do have this real complexity that you should take account of if you actually use this data. And then you can see there's a longer discussion here that's quite interesting from Ernesto Amaral. So I encourage you to take a look at it if you're interested in this material, but for the sake of this class, you should just know that we don't have actual simple random samples. So I wanted to wrap up by briefly discussing experiments. So we've been talking a lot about samples here, and samples are cases where we draw people from the population with some amount of randomness. But one thing you might be interested in is a situation where you don't need to rely on this randomness and you can just plan an experiment. The reason for wanting to do an experiment is pretty straightforward. Causality is easier to establish with experiments, but they're a lot rarer in human sciences than our observational studies because of ethical and metaphysical issues. So we can't assign people class positions just to see how it affects their mental health, for instance. We can't assign adults value on parents' education. That would not only be wrong, but also physically impossible. But we still do rely on the logic of experiments to think about what it would mean to be able to make an inference. And when we do things like multiple regression, which we won't do in this course, but we're setting you up in this course to learn that, we'll mimic the effect of having these randomly divvied up treatment and control groups in multiple regression. And in fact, we call these other factors controls because they're basically like controls in experiments, even though they're not strictly speaking controls, they're just other variables. If they are unobserved, they become potential confounders and they wreck the analysis. So the nice thing about experiments is they let us avoid confounding. We can't control levels of certain variables in human experiments, but we can balance those across treatment and control arms, which isolates the effect of the treatment. But in observational studies, this balance is rare because covariates are usually not balanced across treatment and control. And worse, there's almost no chance that some of them won't play a strong role in the outcome. So here's what that might look like. Let's suppose you're interested in some outcome, say someone's rate of cancer. And if you then think about a treatment and a placebo that say maybe treat the cancer, and you could somehow actually control for, say, someone's class status and their level of education and their blood pressure in this group. So you could make sure that these were the same across the groups. And then you only have one difference, the treatment versus the control. We would say that that gives us pretty strong evidence that, okay, it's the treatment that actually cause the outcome because otherwise the control group was identical. The problem is that in practice, if you think about some treatment, let's say maybe working in a factory that's filled with fogs and fume and things like that, and you say, okay, well, I hypothesize that it's working in this grimy factory that causes cancer. Here, the treatment is not a good thing, it's a bad thing. The problem is that because these other things here do affect the outcome, it could be the case that if you don't know for sure that they're balanced across the two groups, that those are actually affecting the outcome. Well, would someone's class and education and blood pressure be the same if they work in a grimy factory as if they don't? Probably not, because those two things are associated. So importantly, in an actual study, in an observational study, there's probably an association between these covariates or confounders and this treatment. And so we have to be able to control for them in order to isolate the effect of the treatment. If we don't, we can't be sure that this isn't affecting the outcome, because, and not only that, but it could be entirely responsible for it. And we just can't know because this group here that's got the treatment will have different levels of these covariates than will this group that's got the placebo. The nice thing about experiments is that, as I note here, other variables do affect the outcome, but in theory, they should affect it by the same amount between the two groups if we have this balance. And then here's a little bit about what is meant by randomized controlled trials. And this is kind of just giving you a little bit of extra information about some of this jargon. I'm not going to walk through this in too much detail. I just wanted to note at the very end of this part of the lecture, since we're not going to have time to cover it too much in this course, that if you see phrasings like these, so in our analyses of job satisfaction, we control for several family background and attainment characteristics, or I estimate the union differential by regressing earnings on a union dummy variable and a set of control variables, and so on and so forth. These are basically uses of multiple regression to simulate experiments. And this is what those models look like. These models are the workhorse of applied social science, and they're important to learn at a higher level if you're interested in statistics. And notably, we can use them to control for variables that are basically nominal variables, and you may wonder how we can actually use nominal variables in a regression analysis, and you'll actually see in the next lecture that we turn them into dummy binary or indicator variables, and then we can use them in a regression. And that's where this lecture stops, so I hope you stick around and watch the next lecture. Thanks for watching.